All right, so let's look at this entire cycle here. Okay, for the cycle AB, BC, CD, and DA, right? Okay, find Q, delta U, and work for each process. Find the net work done and find the efficiency of the cycle, right? Okay, so let's make a little table here. We'll have cycle AB, BC, CD, and DA. Da! All right. And then let's draw some straight lines. Look how straight I can draw lines. I must be talented. Either that or I know that I can hold the shift key down. Could be that, I don't know. All right, so it's sort of satisfying, right? Okay, so the Q is here, and then delta U we're going to put there, and work we're going to do there, right? Okay, so let's figure this out. So AB, the work, let's find the work. The work is pressure change in volume, right? So that is 7E5. Notice that these are times 10 to the fifth. That's 7, right? Okay, and then our change in volume is 1, 2, 3, positive 3 E, and these are times 10 to the minus 3, right? Okay, and that is positive 2100 joules, right? So AB is positive 2100 joules, right? Okay, I better leave a little space here, wangy, to find the sum. All right. Okay, now let's figure out for AB, let's find, this is our work, right? Remember that our change in internal energy is just 3/2 P delta V. So I'm going to use that. By the way, we don't, for this one, they didn't tell us how many moles we have or even the temperature, and we don't need to know, which is kind of weird. Okay, so 3/2 times this, right? Remember, this is P delta V, so 3/2 times that. So 7 E5 times 3 E minus 3 is still 2100 times 3 divided by 2, and that's 3150, right? And then if we add the 2100 to that, because remember that Q equals this plus that, right? Okay. If we add those together, if I add this to this, right? Okay, I'm going to get that it's 5250. Right, so during this process, right, 5250 joules of heat flow in, right? It does 2100 joules of work, and it stores 3150 joules of it as internal energy. That's kind of fun. It actually does, it increases its internal energy more than the work it does, right? Which, I mean, you know, just that's what it does, right? Okay, so for BC, the work is pressure change in volume, right? So the pressure changes, but the change in volume is 0. So that's 0, right? So BC isochoric processes have no work, right? So the work for BC is 0, right? But there is a change in internal energy, right? Heat is going to flow out of that thing, right? Okay, so let's figure that out. The change in U is 3/2 change in pressure times the volume, right? Remember, that's the shortcut. Do it. You use the shortcuts, baby. Okay, so 3/2 times our change in pressure is that we go down 3 times 10 to the 5th pascals, right? Let's see, 1, 2, 3. That's times 10 to the 5th. Okay. And then our volume is 5 E minus 3, right? These are E, I mean, by E, I mean times 10 to the, right? Okay, so 3 divided by 2 times negative 3 E5 times 5 E minus 3, right? All right, so that's negative 2250, right? The change in internal energy. So it gets colder, right? Okay, so that's negative 2250 joules, right? So now the question is how much heat flowed out? Well, you know, this is basic math, right? This plus this is negative. So basically what happens is this 2,250 joules of heat flow out and the pressure just drops, okay? All right, so that's pretty good, right? And then let's look at process CD, right? The work is pressure change in volume, right? And the pressure is a constant 4 times 10 to the 5th, right? And then our change in volume is 1, 2, 3, negative 3e minus 3, right? So 4e to the 5 times negative 3e minus 3 is negative 1200. Right, so the work for CD is negative 1200. Right, remember that the change in internal energy is 3 halves. That's a weird 3. 3 halves P delta V, right? So that's going to be 3 halves times this. So times 3 divided by 2. That's negative 1800. Okay. So in this process, 2250 of heat flowed out, right? In this process, we'll figure this out here. This is negative 1800, right? So what does that add up to? Is that just 3000? That is negative 3000. This is all wasted heat, right? So 3000 joules flow out here, right? Okay, so let's see. All right, we're almost done. We're almost done. So let's look at DA. DA, process DA, right? Work is pressure change in volume, which is 0 because there's no change in volume, right? Change in internal energy is 3 halves delta PV, right? So it's 3 halves. Our change in pressure is positive 1, 2, 3 times 10 to the 5th, right? And then our volume is 2e minus 3, right? It's getting slow, right? The more writing there is, the slower this pen is. It's just weird. 3 divided by 2 times 3e5 times 2e minus 3. And I get 900. Right, so the change in internal energy is positive 900 joules. Right, the work is 0. So how did that happen? How did the internal energy rise by 900 joules? Well, 900 joules of heat flowed in. Right? Okay. So if we look at the total amount of work done, right, the total amount of work done here as we add this up, this is positive 900 joules. Positive 900 joules, right? Okay. So that is the net work done, right? Which, by the way, we could get 900 joules by finding the area of this thing, right? Okay, the area is 3e5 is this dimension here, right? And then this dimension here is 3e minus 3, right? And that gives you 900 joules. The fact that it's clockwise makes it positive, okay? Because remember, it's doing work at the high pressure, and we're doing work on it at the low pressure, right? So it's a net positive thing, right? Now, if we figure out the Q in, right, the total heat flow in is this, and this is what we have to do for efficiency, right? It's this and this. This is the amount of heat it uses, right? So we give it this plus this amount of heat, right? So Q in, I'm not adding all of these columns. I'm not adding this guy. I'm not adding that guy. That's just waste heat. And we don't care about that, right? Remember, efficiency is work done divided by the total heat used. So the total heat used is this plus this. So 5250 plus 900 is 6150. Okay? The total heat that flowed in is 6150, right? So the efficiency is work divided by Q in, right? So that's going to be, it's getting there's so much writing here. That's going to be 900 joules divided by 6150, okay? So 900 divided by that guy is 0.146, or about 14.6% efficiency, right? Okay. So remember, for efficiency, we figure out the total heat that flowed in. We don't care about the waste heat. We just care about what flowed in from the boiler, and then we go work divided by heat flow in. Okay. Now, interestingly enough, right, if we actually figure out the net, if we sum up this column here, we should get 900 joules, shouldn't we? Let's just see. Okay, so 5250 minus 2250 minus 3000 plus 900. We get 900 joules, right? And that's because the difference between the total heat that flows in, and then the heat that flows out is, of course, the work that it does. Okay. Yeah. Okay. So if they ever ask you for the efficiency of a cycle, do something like this. Set up a whole thing like that. And obviously, if you do enough of them, you could do a shortcut. Like we didn't care about this total heat flow out, right? But if it said what's the total heat wasted, you would add these two, right? That's the heat that's wasted that flows to the low temperature reservoir. Total heat that flows in from the high temperature reservoir is this and this, right? Okay. Carnot cycle is actually simpler in this case because the heat flows in during one cycle and all of it flows out during a different cycle. All right.